Hello and welcome to part 3, and the final part indeed, of our Piper mini-series, looking at how we can use Piper to calculate inlet pressure drops, back pressures, all that kind of good stuff. So part 1, just to remind us, we modelled the valve. Part 2, we've done our discharge pipe work. Part 3 is all about this inlet pipe work, and this is where it gets a little bit more interesting. But the first thing we need to do is put it onto the model. So we're going to have our contraction. So that's our contraction from our vessel into our inlet pipework. I'm actually going to put a contraction on here as well. So that's going to put my contraction down into a relief valve. So I'm going to go from, actually I'll put the numbers in. So I'm going to go from a D303, which is 1.7 meters, down to, I'm going to go for a 2-inch pipe, 2-inch shed quality pipe work. Or we can put some mild steel, slightly corroded. What else would you use? So that's our initial contraction, which we need to model. We've got our relieve pipe work, so our 2-inch inlet pipe work. We need to give it, again, we can just pick one randomly. Give it a length. Now this bit can be really key for doing this. So when we're looking at inlet pressure loss, we need to keep that angle to the horizontal as 0. Now, in this case, it's not going to make a huge amount of difference because we've just got vapor going through, so it's a bit of a simpler case. But if you had two-phase flow, then the piper will calculate the static head change, and that will appear in the pressure calculations. What we're trying to do is calculate the irrecoverable losses due to friction. Static head change is not an irrecoverable loss. What you would need to do if you've got significant static head change is change the set pressure of your relief valve. But we don't take it into account for our inlet pressure loss. We need to make sure that angle to the 0, angle to horizontal is 0. So we are only going to calculate the flow through that horizontal pipe, and eventually we can compare stagnation pressure to stagnation pressure, and the difference between the two is what we've lost due to friction. So that needs to be 0. So that goes in there. Let's make that 2 meters, and then that's there. And then we're going to connect this onto here, but this is our contraction. And let's just make that 1.5 inch before I connect it up. And then I'm going to do my little connection in here and connect it. So like that. So just to explain the connections a little bit, when I drew or pulled this contraction on, these two were automatically connected. That's because that's highlighted, that's toggled. You can toggle that off if you don't like it automatic connecting. It didn't know obviously to connect that to that, so I can just pull a little connection in. You can have a one with a bend in if you want. So that's just drag and drop type stuff. So we connected it up. So we've now got our model. Let's just double check it's okay. So we've got 1.7 meters into our 2-inch, reducing down into our 1.5 inch valve. That's the model of our orifice. And then we've got 3-inch, expanding to 4-inch to discharge. That's a discharge to atmosphere. So a very simple system, but we can just check that's all okay. Happy with that. We're going to press calculate. And again, the first thing I want to do is just check my flow rates hasn't changed significantly. Just keep double checking that, because we're trying to model the pressure losses and the back pressure due to the right flow, in this case the rated flow through the valve. So I've got 2688. I can go back to 2699. So 11 out in 2,500. I'm going to be relatively comfortable with that. I don't want to start iterating too much, but you could iterate a little bit if you wanted to squeeze it a little bit closer. I'm checking I've got a choke, so I've definitely got a choke in my valve. I'd expect to see that, particularly at 6-bar gauge, so that's a good double check. I can look at my static pressure. So again, if you look at the part 2, we talked about this, the back pressure. So your back pressure is the flowing pressure or the static pressure at the outlet flange of your valve. That's technically this one here, but it's a negative number, and that's fine because I'm in bar gauge. That's to do with the flow going through. So we've expanded, we've got a lot of flow, we've pulled the pressure down a little bit. I say in that situation, I would quote this for the reasons you'd see in part 2, but that's technically the right answer. But fundamentally what we're trying to do is that less than 10%? 6-bar gauge, relief device, so back pressure 0.6 bar. We're way below that, so I'm absolutely fine with that, not a problem at all. And that's really the key to it. We're just trying to see, have we passed 10% or not exactly what the number is fundamentally. So now we're looking at our inlet side. So we've got 6.6 bar gauge here, so our relieving pressure, and then we've got 6.5 bar gauge going into our valve. Now we could take one from the other, get 0.1, but that's not our irrecoverable losses due to friction. That's a stagnation pressure. That's a flowing pressure. So we need to do a little calculation, and we are going to work, and eventually this will be in Piper, but for the time being, the workaround looks a little bit like this. So go back into Capri. I've added a continuation sheet, so just to show people where that lives. I'll just move the annoying little record bar out the way. Administration. And you've got some continuation sheets, you've got the title sheet here. So again, you can carry on making the calculation look nice. These are just blank sheets. You can type your own things in there. But it helps produce that pack that looks neat and tidy. I've also color-coded the cells to make them look like Capri cells, so it kind of follows the same format, makes it look nice again. So what we need to do for that second pressure, that pressure going into our valve, we need to convert that static pressure into a stagnation pressure. And one of the ways to doing that is this equation here. So we've got static pressure plus a density times our velocity squared over 2. So we can calculate that, add it to our static pressure, and then we're going to be in the right place. We're going to get the right value. So what we're going to do, we can look at the Piper results. Now, we've got our conditions here. We've got mass vapor fraction. Now, in this case, we're just on single phase vapor. But here, if it's 2 phase, it would show you what your vapor fraction is. So we're going to put 1 in here. And then I've made that calculate. So obviously, liquid needs to be 0. And then I need my vapor density. So I can go here to my physical properties. I'm going to look at my contraction now. I need to just remember which one it is. So it's number 3 of the 4th point, but pipe section 3 is the one I'm looking at. So pipe section 3, this one here. So a vapor density of 20.52. Let me put that in there. Obviously, I haven't got a liquid density, so that's fine. But if I did have, you would have the details. There you go. Liquid density would appear in there. So you'd put that in, obviously. Now, this is 0 at this point. Because what we're trying to do with this bit here is to create a homogeneous density and average density. So that's the same as that. It's all vapor. So our static pressure at the source, then we need the static pressure at our relieving valve. So let's go back. So, and this is where again we need to be very careful of units. It's easy to get these wrong. So, again, it's probably maybe easier just to change the units, make sure that we're getting the right numbers in the right place. So I've got 761. 761, let's type that across. 7.61 bar absolute. My static pressure in my relieving valve, we said it was this 7.51. And of course, you make that as accurate as you want, with it, doing this fairly quickly. If you had 2 screens, you could, instead of flicking between the 2, you could get it a lot more accurately. Velocity. So again, I can come across, and I've got my homogeneous velocity here, so 22.92. So that's done this calculation for me. I've converted this into pascals. So that is taking that number, converting to pascals, doing our calculation, and then putting it back into bar absolute. So just playing about with the numbers and the units, make sure it's right. But you can see our static pressure was 7.51, but our stagnation pressure is 7.56. So we take that number from that one to get our inlet pressure loss, which is 0.05 bar. I've got a 6 bar gauge relief valve, and I really should put bar gauge on there before people shout at me. And then we've got an inlet pressure loss of 0.7%, less than 3%. We're absolutely happy. But that's how we need to handle that inlet pressure loss and how we convert our static pressure into stagnation, and then we can compare our two stagnation pressures. And there we go. Enjoy.